Hello and welcome to a discussion on the epsilon delta proofs for limits. We're going to first talk about why, some of the tricks that are hidden behind the scenes, and the men behind the curtains. That's a Wizard of Oz reference. And then we'll do an example of it with linear, quadratic, and radical to see how these tricks and tips, and certainly why we're doing them, help to understand this epsilon delta and how to write proofs of that. So first of all, we talk about limits. Now the concept of a limit is when you're, let's write it out, the limit as x approaches x naught of f of x equals L. That's a number. L is a number. Now notice this x right here. This is actually a variable. That's important to note. You're like, of course, what else would it be? That is a constant. That's a number. Okay, that one doesn't change throughout the entire course of the proof. And that is a number. Yeah, that's a constant. And that guy right there, that's a function. Okay, right there. So let's write out what this definition means. It starts off by saying, given epsilon greater than 0, there exists, that's that symbol right there, there exists a delta greater than 0 such that, I'll do an ST for such that, when x minus x naught, or you could have an A there, that's okay. When the absolute value of that is less than delta, that will imply that f of x minus L is less than epsilon. Okay, now, first of all, a couple of things with this definition. We understand the concept is as x gets closer and closer to x naught, that the f of x's that correspond to that will get closer to L. So this is how it'll be drawn on this on a graph somewhere. You'll have this function going up here like this, and here's your little x naught. When you stick in f of x naught, now it doesn't actually have to be defined there. So there could be a hole right there, either filled in or open like that. Doesn't really matter, and that's the whole point, is that it doesn't really matter. But that right there, that is your limit L. So this is an f of x naught if it's continuous, and if it's not, then there could be a hole there, whatever. And so writing this in terms of the epsilon delta is kind of important. So it says given epsilon greater than 0, and notice epsilon is the distance between the f of x's and the L. So they're saying there's this epsilon bound around the L. Here's epsilon up, epsilon down. And so if you draw this straight across like this, they're saying given any epsilon, now it could be huge, it could be small, but obviously we're going to be interested in the very, very small ones, because the limit is as you get closer and closer to this x naught, the f of x of all those x's are going to be very, very close to L, which means you've got to be scrunched within here. So this is where this definition comes from. This statement right here is like a horizontal bound around L, and it says this is arbitrary. It can be given arbitrarily. It can be 1/billionth, it could be 1/trillionth, and no matter how small you get, so this is actually for all epsilon greater than 0. So any number that's positive in any sense. Now, the reason that's so important to understand that is because we're saying that there's a delta. So once you pick that epsilon, you can see that right here, if you go, let me see, and let's do it right here. There's a delta such that if you go delta up and delta down, all of these x's, it forms kind of a rectangle such that all of these, now remember x is a variable, all of these x's here have f of x's in this level. So the points of the graph fall in this rectangle. So once you give a horizontal band, we can find a number based on that epsilon that gives us this vertical band that says all the x's in here, boom, all of them, all of the f of x's, I should write these up here, all of the f of x's fall within that rectangle. And that's important. If this delta goes too big, you'll notice, boom, we're going to be outside of it. So being able, that's how it's scrunching in. When we say, oh yeah, as x gets closer and closer to x naught, that's the delta. We get closer and closer to L, that's the epsilon. So we're saying an arbitrary small epsilon, we could find a delta. And the important part is that this delta really depends often on that epsilon. So really, delta is going to be some function of epsilon. That's how we can establish that we always have a delta that works. Okay, now let's get into the nuts and bolts. But that's why this definition, which seems to have nothing at all to do with, as this gets closer and closer to this, the f of values get closer and closer to that. That's what it's actually saying. This is the f of x values getting closer and closer to L when x gets closer and closer to x naught. And remember, x keeps moving. So these f of x's, that's that right there. And if it's continuous, that x naught goes there. All right, so now we've got that background. Let's look at the proof and why we need certain tricks. Notice that we are dealing with absolute values and inequalities. That's the important point. That we're some of the tricks and behind the scenes fancy footwork that we're going to do are dealing with absolute values and inequalities. So yeah, if we can find a bound on something, that's going to be very valuable for us to be able to say, oh, look, we can scrunch this into this box, and that will show that we've proven a limit. Okay, the other thing I want you to note is this is a little connection to the first shall be last and the last shall be first. Notice that the epsilon is given. This is the independent parameter that is handed into the problem, and then we have to find a delta from that. Okay, so it kind of depends on that. However, notice that the such that reverses the order, such that whenever this condition is met, and this is the condition that is met first, and that it will imply the condition met by the epsilon. So given an epsilon greater than 0, there exists a delta. That delta depends on what epsilon was given. However, when you write the such that, we use that delta and show, and this is where the proof comes in, we're going to show that if we meet that criteria by this cool delta we found, that it will lead to the end result that all of the f of x values are close enough to the L. So there's a little bit of first shall be last and last shall be first there. Given an epsilon, that's where we start, but that is where we end. And at the end of the proof, once we show it's less than epsilon, that's when we're going to be done. So the definition gives in this indication of how we go through it. Okay, let's look at a few of the tricks and behind the scenes stuff that we're going to need to do. Okay, the tricks, what I call the curtains. Don't pay attention to the man behind the curtain was actually when the Wizard of Oz was found out to just be a guy with a whole bunch of doohickeys and gadgets to make himself look powerful. That's kind of where that comes from. Notice that we're given a random epsilon and we have to find a delta. So the first is behind the scenes or behind the curtains, the fancy footwork. You need to find a cool delta. And it is not the same as using that special delta to write the proof. To proof. Yeah, okay. That's all right to say that. But behind the scenes, you've got to find that delta. That's not a figure 8. Let's see if I can get that better. We need to find a cool delta. And this is going to be completely backwards of using that delta to then make this proof come out exactly right. So that's one thing. Find the cool delta. And what's going to be amazing is this statement will, in all of our examples, is going to be manipulatable into something like that, which is going to tell us exactly what delta we want to use. Which is weird because then when we write the proof, we're going to go the other direction. So that behind the scenes, that's the first trick that's going to happen. The other thing, we'll get to those when we get down to some of these others where we're going to use different tricks to bound the x minus x naught or something similar to be able to construct that cool delta. And then we're going to use all of our behind the scenes work to then justify the proof. All right, let's look at a couple of examples. For our first example, we're going to do linear and show you how this works. So f of x equals 3x minus 8, and we're going to prove that the limit as x approaches 7 of 3x minus 8 equals 13. Now, if you notice this, 3 times 7 is 21, minus 8 is 13. That's how you would compute that limit, but we're not computing the limit. We are proving that that limit is exactly 13, and we're going to use this epsilon and delta proof of it. So the first thing is we're going to find this cool delta. So the idea is we want this. Okay, we want this guy, which f of x, so we'd write 3x minus 8 and then that's the f of x, minus 13, okay? This guy right here, we need to make that less than epsilon. That's our goal. So I'm going to hold off on that for just a little minute, but yeah, we need to make that. Let's write that down, epsilon, like that. Okay, so the idea is we need to somehow connect this with our mathematical algebra skills to be something like x minus, and then our x naught is a 7. Now remember, the x's are all moving here, and the 7 is a constant. And we need that to be next to something with an epsilon. So an epsilon to the 5th or whatever. So that's our goal, is to match it. And then once we figure out what that guy is, that's our magic delta that we're going to stick back over here and use in a proof. Okay, so let's undo that and let's see if we can make it come out to an x minus 7. Okay, so here we have an absolute value of 3x minus 21. All right, that's less than epsilon. And then let's factor out a 3. X minus 7. Oh my goodness, look, there's an x minus 7. How convenient was that? Yeah, this 3 is a positive number, so we actually have a 3, absolute value of x minus 7, less than epsilon. And then we're like, oh my goodness, x minus 7, less than epsilon over 3. Oh my goodness, if we use that as a delta, can you see how we can use it? That is like a magic number. And so this is how it'll actually look. On this, that was behind the scenes, and we say, all right, so we're proving it. We say, given epsilon is greater than 0, define delta to equal epsilon over 3. And if you haven't done this side right here, you have no idea where that came from. You're like, what? And you're like, just trust me, I know what's best for you. So delta equals epsilon over 3, and then you're like, oh yeah, so when we have absolute value of x minus 7 is less than epsilon over 3, well, what happens? Well, we just reverse this process, because we're trying to show that when this happens, yeah, we get 3x minus 7 is less than epsilon. Well, that's jump the 3 in because it's positive. You can do that. That's 3x minus 21 is going to be less than epsilon. Well, that's 3x. That's definitely minus 8 minus 13 is less than epsilon, which is the f of x, and that is the L. So when you see that that's the f of x minus L, when this happens, we can conclude that that is there. Boom. And you write something like, therefore, I don't know, put 3 dots. Therefore, the limit as x approaches 7 of 3x minus 8 equals 13, something like that. As soon as you get that that is less than epsilon, whenever you see that, and you're like, these are kind of the same. Well, they're the same algebraic process, yes, but totally different in conceptual idea. Here, we had a random, and we showed that there was a delta, such that when delta was this number, boom, we got that it was close enough to 13 all the time. Epsilon could be a billion. Well, a billion over 3 is what delta is, and it will for sure be in that box. Excellent, so that was linear. Before we go, we should note, there may arise a question, will this always happen? Short answer, yes. I'll discuss that in the quadratic, but yes, this will always pop out nicely. Okay, before we do the quadratics, there are a couple of tricks that we want to make sure you note here. First of all, I'm going to use a random variable down here. We'll just put the tricks down here that we collect. First of all, that if you have something like y is less than 8 and is greater than, I don't know, a 4, you can actually, if this happens, you can make this claim that absolute value of y is less than 8. Now, you're like, where did you get that? Those are not the same. They're not the same statement. This is only a one direction arrow. And that's important to note. When you have, is this true? If y is between 4 and 8, then absolutely y is less than 8. But it doesn't go into the negative. So you can actually make this statement. That is a weird statement. Or if you had something like y is less than -2 and it's greater than -7, the absolute value of y is definitely less than 7. Okay, this is an interesting note. Again, this arrow only goes one way. If y fits these conditions, then y fits these conditions. It doesn't go the other way around. For example, 0 works that it's less than y. 0 is less than 8, but 0 does not fit this condition. So the condition doesn't go backwards. This would be the same as saying y is greater than -8, less than 8. And that's how we normally go, is from here to here. But you can actually take an inequality like this and make a condition like this. That is a trick that many people will not think about. So that's the idea here. Let's look at a quadratic. We're going to take any quadratic here, and we're going to prove that, say, f of x equals, I don't know, x squared plus 7x minus 1. There we go. And let's take the limit as x approaches, I don't know, any random number. X approaches 3 of this guy of f of x is going to equal, in this case, 3 squared is 9, plus 21 is 30, minus 1 is 29. Like that, right? Okay, double check. 9 plus 21 minus 1, 29. Yes. So if you stick it in, yeah, that's it. So now we're going to prove it. So over here, we're going to say, given epsilon is greater than 0, we are going to choose delta. Let delta equal, and we've got to fill in that blank. That is our goal. So now we're going to go behind the scenes and find the cool delta, but this isn't the proof. All right, so we're going to start off with where we want to end up. We want to end up with x squared plus 7x minus 1 minus L, right there, minus the 29, has to be less than epsilon. That's where we want to end up. So let's keep that in mind. So this is going to be x squared plus 7x minus 30. This is going to be x plus a 10 and x minus a 3. Oh my goodness. There's an x minus a 3 and there's a 3 that remember, we've got to get down to something like x minus 3 is less than something with epsilons in it. We're going to have an epsilon or a times this or a divide by this or something. We're going to have an epsilon in there, and that is going to be our delta. So I'm going to leave that box right there. That's what we want. Nah, I don't know if I'll have that much room. Okay, so that's where we're going. Well, look, there he is right there. So we have x plus 10. Let's write that out, x plus 10. And we have an x minus 3 right here. Now, our goal is to have this less than some form of epsilon here. So I'm actually going to hold off on this guy for just a moment, and we're going to insert something that is going to be less than the epsilon, and then that will force that to happen. So this is another one of the trick. Inequalities are transitive. If you can have this less than something that is less than epsilon, then certainly epsilon is going to be greater than the whole thing. So we're kind of inserting that. We're like, what? What did you do? You can't just erase that. No. I'm doing the behind the scene. Don't pay attention to the man behind the scene, behind the curtain right now. So the idea is we want to put a bound on this guy right here. So this is where we are actually going to be using some fancy footwork here. So we know that we want x minus 3 has to be less than this delta. And that's what we're going to use up here. So we are interested that when epsilon gets really tiny and delta gets really tiny, we zoom in on a limit. So really big deltas they're not going to be relevant. So this is the trick that is going to happen. We are going to say that delta is going to be at least smaller than 1. And this is how we write this. Delta is going to be the minimum of 1 and this secret epsilon dependent number. And this is fascinating. So we're saying delta is always going to be less than or equal to 1. That if epsilon's so large that we could have a delta that's 2 or 5 or 8, well, Dude, just use delta equals 1. Then it will all the x's in there will fit. It'll work because all the x's within 2 plus or minus would work. So if we choose a smaller one, 1, of course, 1's going to be irrelevant once we zoom in really, really tight. But this is a way of throwing out possible big deltas. And so this is another way of saying that delta is always less than or equal to 1. This is important. So watch what we're going to do here. We're going to take and split this off right here. And we know that x minus 3 is always going to be less than delta, which is going to be less than or equal to 1. We got that? So this means x minus 3 is always less than or equal to, less than 1 and greater than negative 1. Okay, that's what the absolute value of x minus 3 being less than 1 means. See this transitive thing? If it's less than delta and delta is always less than or equal to 1, I kind of made that up. Good. Now, I'm going to make an x plus 10 in here. So I'm going to add 10. I'm going to add 10. I'm going to add 10. And I now have so I'm going to add 13, add 13, add 13. What just happened here? I now have 12 is less than x plus 10 is less than 14. You're like, okay. Now, see this trick right here that I used? This means that the absolute value of x plus 10 is definitely less than 14. Fascinating. Fascinating. So here's where this got, you're like, wait, is this fancy footwork? It kind of is. We're creating what's going to happen. So this guy is less than 14 times x minus 3. And now I insert the, I held off and now I inserted the epsilon. And you're like, what just happened? So because delta is always less than or equal to 1, and I have just made that choice from the beginning of my choosing what delta is, I have now forced that this x plus 10 will always be less than 14 all the time, no matter what delta is, because delta is maximum value is 1, or it could go smaller, but this will always be less than 14. Good. So if I pick that right delta, then bada boom, right here. So now can you see where I can go from this inequality? Keep going from here. I have x minus 3 less than epsilon over 14. And boom! There's my other half of the delta. Goes right there. Okay, that's the behind the scenes. Now let's look at how the proof works. So delta is going to be the minimum value of 1 and epsilon over 14. And let's see how this works out. So then for all x such that x minus 3, okay, so again, we're using this a value is less than delta. Okay, this implies, and it implies two things. Okay, so let's reconstitute this guy right here, that when x minus 3 is less than delta, which is less than or equal to 1 because of how we've constructed delta. Delta is a number that is less than 1 and less than this. So it's the minimum of these two numbers. And so if epsilon over 14 is 0.7, then delta is 0.7. And if it's bigger, if epsilon is 38 or 28, and so this number is 2, then we're going to pick delta to be 1, fine. But delta is always going to be smaller than or equal to 1, regardless of which one of these we pick. So that means, yeah, just rewrite all this guy. So we've got that x minus 3 is less than 1 is greater than negative 1. Oh, I don't need the absolute value. Sorry about that. X minus 3 is less than 1 is greater than negative 1. And then we've got, yeah, add 13 to all of the sides. You have a 12. We're just rewriting what we did here. X plus 10 less than 14. And then we have that the absolute value of x plus 10 is less than 14. All right, so that's one place we used it. And so then we're going to say delta is the minimum of these two right here. So we know what happens if it's always less than 1. And now we worry about the fact that when we zoom in, and this is going to be the primary delta that's going to be in, that we're going to even prove it. So here we go. We know that this is going to be less than delta. And we also, so delta is always going to be less than or equal to that. So that implies that x minus 3 is always less than epsilon over, absolute value of the x minus 3 is always less than epsilon over 14. So now if we times by this on one side, and we times by the 14 on the other side, can you see what we did? We kept this inequality because we times by a smaller entity on the smaller side and a larger entity on the larger side. Which obviously you're like, oh, well, yeah, we can do that, I guess. Why would you do that? Oh, why would we do that? Because this then gives us the absolute value of x squared plus 7x minus 30 is less than, oh, look how nice that is. That's epsilon. And then this is, of course, x squared minus 7x. What was our thing? Minus 1. Minus 29. Oh, let's write that a little bit better. Less than epsilon, which is, there's our f of x. And that is the L, and then you write it pretty. Therefore, we have just said that when x minus 3 is less than delta, if you choose delta to be this fancy thing, that will imply that x minus 3, for all of the x's in that little realm, the f of x's are in this little band of the L, which proves that the limit as x approaches 3 of f of x, yep, does indeed equal the 29. Good. QED, put the little square in there and you wrote your proof. Excellent. But you see the behind the scenes, you're like, well, it's kind of backwards. Yes, we had to find that cool delta, and we used an additional coolness on the delta, that our delta was always less than or equal to 1, at least that. And it's going to be less than or equal to, yeah, notice that when we put delta is less than or equal to that, or an epsilon over 14, it gives us that delta, we can always use the fact that delta is going to be less than or equal to epsilon over 14. We can use both of these conditions because of how we define delta. And we used one of them to do this and one of them to write the proof. Excellent. Okay, we'll do one more really quick, and I'll use those tricks again with another quadratic. So let's do another one. F of x equals 3x squared plus 4x minus 1, and let's do the limit as x approaches 2. There we go. So we have 3 times 4 is 12, plus 8 is 20, minus 1 is 19. F of x is going to equal 19. Okay, so yeah, we could just stick it in. It's nice. It's a polynomial. Good. So again, let's do it, and let's find our delta. We want to start off with the 3x squared plus 4x minus 1 minus 19. That is what we eventually want to have less than epsilon. But we'll insert that guy later once we have manipulated it sufficiently. So let's see what we have here. 3x squared plus 4x minus 20. And, okay, that isn't looking really good, but let's see what happens. We're hoping to get absolute value of x minus 2. So let's check and see if we can do x minus 2 in here and see what the other guy turns out to be. It better be a 3x and a plus 10. And you're like, wow, does that really work? 3x squared minus 6x plus 10x minus 3. Yes, indeed. And again, here we get asked, will x minus 2 always be a factor of this? And the answer is yes. You need to understand that that is part of this. If this is a polynomial at all, and this is the limit, when you subtract that, the limit from here, you will get a 0. And if it's a polynomial in here, that polynomial, if 2 is a 0 of this function inside the absolute values, then that means x minus 2 will be a factor. That is a theorem, and that's why it always comes out so nice. So we're going to do this and take this cool delta thing. And again, we're going to do this delta equals 1 and write down over here. All right, so now we're going to use that trick. X minus 2 is going to be less than 1. Right? It's actually less than delta. Let's put that in there, which is less than or equal to 1. And we use this half of it to see if we can get that other half to put a bound on 3x plus 10. So this is x minus 2 is less than 1. And again, that was the transitive property. So x minus 2 less than 1, greater than negative 1. And so what we're going to do here is add 2 to both sides. So we get 1 less than x less than 3 times everything by 3. So we get 3 less than 3x less than 9. And add 10 to all sides. 13 less than 3x plus 10 less than 19. Hey, look, that means the absolute value of 3x plus 10, using this guy right here, is going to be less than 19. Oh, that's nice. So that means that this up here is going to be less than 19 times x minus 2, less than epsilon. That's what we're trying to get. So x minus 2 less than epsilon over 19. That is our special delta. Delta is always going to be less than epsilon over 19 as well. So that's what we do. Say given, we're in our proof, we're going to have given epsilon greater than 0, we're going to let delta equal the minimum of 1 and epsilon over 19. Whichever is smaller, that'll be great, but delta will always be less than or equal to that and less than or equal to that. So for one purpose, if that, then then for all x such that x minus 2 is less than delta, we get two different things. So we get a right. So let's write both of those. So we get that x minus 2, we're going to rewrite that whole thing. So I'll zip through it really quick. Less than delta, which is less than or equal to 1. So notice we're using the minimum 1 here. And so that means that x minus 2 is less than 1, greater than negative 1, dot, 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 gives us that 3x plus 10 less than 19, greater than 13, which means that the absolute value of 3x plus 10 is less than 19. And now we're going to use that up here. So we know that if x minus 2, notice we said it was less than delta, which is less than or equal to that, less than delta, which is less than or equal to epsilon over 19. And again, delta has to be less, both of these have to be true if delta is the minimum of those. And we just picked which one was handy. So we get that absolute value of x minus 2 less than epsilon over 19. Now we times by this inequality, times by the positive 3x plus 10 here, and the 19 there, and we maintain that inequality. Notice we made this one bigger, this one smaller than that one. So now we have the absolute value of 3x plus 10 times x minus 2 is less than epsilon. For all of these x's, this will happen. And multiply that out, and we're just walking right back up here now. 3x squared plus 4x minus 20 has to be less than the epsilon. And then that means that we've got the 3x squared plus 4x minus 1 minus 19 is going to be less than epsilon. There is our f of x. There is our L. And so we have shown that, therefore, the limit as x approaches 2 of f of x does indeed equal 19, QED. So yes, couple fancy footwork trickery, but this is how you write it out. And somebody may ask, how in the world did you ever get that? Well, there's a lot of stuff behind the scenes. Okay, for radicals, the couple of tricks that we're going to use here are First and foremost, how to rationalize. We usually did it in denominators back in pre-calculus, where you had 5 over the square root of x plus 3. And you had to rationalize that denominator by timesing by the square root of x minus 3, the conjugate, if you remember that wording, x minus 3. And so it ended up being 5 square roots of x minus 3 all over. And then this was a difference of squares. So you had x, square root of x squared, minus 3 times 3 was 9. And note the big key down here is you had no square roots. That's why it was called rationalizing. This is an irrational number. That's an irrational number. This can now be, if x is rational, this is a rational number. And so we have rationalized the denominator. So we're going to use that same idea, but we may rationalize the numerator. But that's the idea, that we can illustrate that we can get rid of square roots in one particular part of an expression should we need to. This also comes with the, it's called the difference quotient. When you do the limit definition of a derivative, you'll use that same trick to rationalize. The second trick is that if you do this 1/2, and you add and you compare it, I'm going to have 1/2 over here. Right now, these are equal. If you increase this denominator by any positive amount, it is now an inequality. That is important to note. And so I'm going to put it like this. 2 plus the square root of x is going to be, the square root of x is always a positive number. Okay, 1/3, 1/4, 1/5. The larger this denominator gets, it is bounded by this. And this is an amazing tool with inequalities. If you can show that you have that just a piece of this, as long as the other part is positive, this is going to be less than just chucking that away. And you get away with that because it's an inequality. Weirdest thing in the world. So let's go through a couple of these. So we're going to say that f of x, give us a square root function, something like square root of x plus 7. I don't know. And we're going to do the limit as x approaches, let's at least make this nice, 2. Limit as x approaches 2 of f of x, square root of x plus 7, equals a 3. So again, we're going to go behind the scenes. We know we're going to try to end up with square root of x plus 7 minus 3 is going to be less than some epsilon. And what we're trying to get down at the bottom is some x minus 2 is less than some cool delta that we're going to put up here at the beginning and start our proof with. So behind the scenes, let's go, and we're like, how could you change that at all? Well, funny you should ask that. We have a really cool piece of our arsenal right now, and we're going to use a different color. We get to use this guy, but on the numerator. We're going to times top and bottom of this by square root of x plus 7 plus 3. And yeah, do the same thing on the top, square root of x plus 7 plus 3. And you may be thinking, what the crap are you doing? Now, first of all, can I do that? Yes, it's a fraction. It's over 1, so I can times top and bottom. What we're doing is we're turning the top into we're getting rid of the square roots so we can combine stuff. So when we times it, again, these are conjugates, so that goes to that, and we get, look at what we have now. This side right here, again, let's get rid of this for just a little minute. So this guy right here, this is square root of x plus 7 times square root of x plus 7 is x plus 7. Then you have square root of x plus 7 times positive 3 is, that's positive 3 square roots of x plus 7. Then minus 3 square roots of x plus 7. They go away. And then minus 3 times positive 3 is a minus 9. Over square root of x plus 7 plus 3. Notice, whoa, look at what just happened. On the top, x minus 2. Unfreaking believable. And you're like, wait, does that always happen? Yes, because when you stick 2 into this as a continuous function, you get 3. That means that when you subtract the function and the limit, 2 is a 0, which means even if it's a polynomial in here, x minus 2 will be a factor, and you can do what we did with the quadratics. Anyway, so let's keep going. This is square root of x plus 7 plus 3. Now I want you to notice this little trick that we got here. This is less than x minus 2. And on the bottom, this right here, yeah, you know what? That just made it bigger. It's just a 3. It's just a 3. Unfreaking believable that you have just a 3. It's a positive number. It would only make that 3 bigger. So yeah, you have this right here. So if this is going to be less than epsilon, boom, toss the 3 up there. And so you're like, boom, 3 epsilon, that's our baby. That's our delta. So let's see how to do it. But notice that was the trick that we had to use, that we actually have a 3 plus something under here. And again, you would technically do this, and we'll show you how to do this. Okay, so given epsilon greater than 0, we always start it, let epsilon be greater than 0 be given, and now we're going to define or choose or let delta equal, in this case, 3 epsilon. Then, for all x such that x minus 2 is less than 3 epsilon, or is less than delta, which is equal to 3 epsilon, we get, okay, so we're going to do this. X minus 2 is less than 3 epsilon. And so we do this. We're like, okay, so we get that x minus 2, divide both sides by 3 over 3 is less than epsilon. And we know that this is larger than x minus 2 over 3 plus some positive number. Now, you can only do this when you add a positive number in there, but this is a bigger denominator now. We have a positive number plus a positive number. It's positive, so we can put these absolute values on there without any problem. It's the same number, didn't change anything. So now reverse do that backwards and times top and bottom by, well, let's write it out a little bit bigger so we can see what's going on. So we have this huge thing, x minus 2 over square root of x, I'm going to keep that in parentheses though, plus 7 plus 3 is less than epsilon. And so now we just pull off that mask. So the trick here is now in undoing that, to make it look nice. This x minus 2, don't write it as x minus 2. Write it as, what did we need here? X plus 7 minus 9, which indeed factors into square root of x plus 7. You're like, how do you know that that does that? Because we made it happen over here. Square root of x plus 7 minus a 3 all over square root of x plus 7 plus 3, and that's all in the absolute values. And we get absolute value of square root of x plus 7 minus 3 less than epsilon. Oh, that was a bad epsilon. So that means there's our f of x. There's our L. For all of these x's that fit this condition, we have shown that this condition will then be met. So therefore, the limit as x approaches 2 of f of x does indeed equal 3. Boom, put the little corner. You are done. Whew. There we go. Those are all the tips and tricks that will help you through all these different kind of proofs, linear, quadratic, and radical. Excellent.